What's up, guys? So this is my analytic number theory lecture. So this is very elementary. So today I want to quickly introduce the Euler 5 function and highlight some basic properties. And I will not give the proof because some of the proof I think is already in the group theory. So I will post my group theory lecture if you want to see the proof. Okay, so remember that our Euler 5 function phi of n is already defined. That basically just all the integer, right? So it's basically a set of all integers that's equal to n greater or equal to 1, where sorry, the mn is 1. Okay, you just count how many of them. Okay, and another definition is that you take the Zn cyclic group and you find its multiplicative inverse, and then you take the number of it. Okay, so theorem. Okay, by the way, and I also say that phi of n is multiplicative if GCD mn is 1. Okay, and the proof of this is via group theory. Okay, the simply speaking is that you can take z of n and z of n, and by Chinese remember the theorem, if mn are compared to each other, you just z mn and you take the multiplicative inverse. Okay, and you get an answer. Okay, so the theorem that I want to say, the first one is that summation 5d dn, right? So you give an n and you choose each factors and take on 5d, give you n. Okay, for all n belongs to integer, positive integer, and the phi of n is basically we have some Mobius transformation that I previously proved. Basically, it's mu of d n divided by d. Okay. Third is that phi is complete multiplicative. Already proved. Third one is that your phi of n is basically summation of p of n minus p product of p of n minus p of n minus 1, where p of m is a factor of n. So this notation means that n is p of n is a factor of n. Okay, and basically you can write this n and the summation of p divides n, where is the prime number 1 minus 1 over p. Okay, and I think this one is already proved, and then let's prove one by one. Okay, so the number 4, I think proving number 4 is trivial, right? Because I know it's completely multiplicative, as it's multiplicative, so I only care about phi of p of m. Okay, this is the number of the right, is a number of the integer, which is less or equal to p to the let's use x, p of m, where GCD of x p to m is 1, right? But GCD of xp to m is exactly of GCD of xp, right? So okay, so all I need to worry, all I need to worry is that I need to delete how many I need to delete the number of which is prime power of the which is a number which is co-prime p. Okay, but p is prime, right? So totally for each p numbers, now I get one which is multiple of p, right? So the number is just p to m minus times 1 minus 1 over p. But because the rest p minus 1 do not have relationship to p, right? So it's p to m minus p to m minus 1. Okay, so this is the combinatorics proof. Okay, so yeah, so I got this, and also this is I already proved in the previous video, so I only need to prove this. Okay. Okay, proof. So our goal is to prove that these 5 functions satisfy this property. Okay, so let's try to prove. Okay, so the idea is that let's say you write A, right, 1 to 2 to n, right? You have a set, and you split into pairwise disjointed. Let's split into the pairwise. Let's say L of D. Okay, and what D means is that it's different D. D is a factor of n, and this D is that m belongs to A. M so there okay this So if M belongs to a set A such that M and N have the D factors. So the GCD is D. Okay, and you can check that this is disjointed. Why? Because why this is disjointed? Right? Because each fixed M, there's only one possible factor, or one possible GCD for each M, right? So different M, different D must come. There's no one M has two D, right? Because once you choose M, the D is fixed, and the only possible GCD for each M with N is at most D. It's just at most comes from this D, right? So this is why this is disjoint union. Okay, now we do a stupid trick, right? We just do this, and I think you guys can see a proof, right? Already see a proof because what? Because it's disjointed, right? So if you take 5n, then you just basically if you take a set, right? Then you get n, and so all you need to prove that this guy is actually this. Okay, right? But this is almost trivial, right? Because you can just write this. You can write m in terms of the, let's say you can write d prime m, right? Such that m prime that's equal to n divided by d is equal to 1, and the satisfied is m prime n divided by d is 1. Okay, so you just divide by d, it becomes this, right? You just write m, let's say you write m equals dm prime, right? So it's dm prime, right? So dd cancel, you get this, and this guy is a number, right? So combine, you just look at this guy and you see, oh, this guy is just phi of n divided by d. Okay, so you get n equals to d divided by n, phi of n divided by d, and then you change your variable, right? Become d divided by n, phi of d. Okay, so this is the Euler phi function, and then in the future, we will investigate Euler phi function. Okay, but let me just mention something which is interesting called the Carmichael's conjecture. This is also I think not yet proved in also in number theory. I think the proof is that I think this theorem just says something which is really weird. It says that if I remember correctly, it says that so given m greater than is greater or equal to 1, greater or equal to something, or greater or equal to 2. Oh, by the way, so the idea is that you can notice that the phi of m cannot be odd, except for it cannot be r prime. Okay, you can check this by yourself. This is weird. The reason is that right, I mean, if you want your phi of m by definition is product of something, right? So, and it cannot be r prime, right? Because you get something prime which is cannot be r, it become -1 or something, right? So which means that if you take any integer, a positive integer, you ask what is the preimage, then it may be empty, right? But one theorem is interesting. This Carmichael conjecture is that you can always find x and y. If phi of n is not non-empty, then you can find x and y difference such that phi of x equals to phi of y. Okay, means that there's no number there's no integer that there's the preimage of the fixed positive integers for this phi function always at least with cardinality 0 or cardinality greater or equal to 2. So that means you can always find x not equals to y such that phi of x equal to phi of y equals to k for given k, if phi of inverse k is non-empty. Okay, so this is a famous Carmichael conjecture, also interesting in the number theory. Okay, just for some simple introduction. Okay, so in next video we will introduce the other like main some different kind of analytic number theory function. See you guys next video.